Hello friends, in this video we are going to have a look at problem 3275, case nearest obstacle queries. This problem actually provides us a good example of using data structure to solve problems. First I'll go through the problem statement, and then we are going to explain the idea, and finally we share two formats of codings. Here, let's look at the problem statement. So there is an infinity 2D plane, right? So we are given a positive integer key, and also we are given a 2D array called queries, which contains the following queries. Each query is a list of two elements. So this corresponds to coordinates. So it's guaranteed that there's no obstacles at this coordinate when this query is made. So after each query, we need to find the distance of the case nearest obstacle from the origin. So we want to return an integer array called results, where the ith element denotes the case nearest obstacle after query I. So the result is -1 if there are less than k obstacles. So notice that k is a fixed constant, and you can understand it like this, or in the function, you can see k is fixed and that I is a running one, right? So note that initially there are no obstacles anywhere. So here the distance is the L1 distance. So here we have two examples, which is very easy to interpret. For example, k equals 2. So we want to find the second nearest. So when we have this first element, so we have less than 2 elements, so we have -1. And then we have this one, so this distance is 3, this distance is 7, so we get 7. And then here we get 2 and 3, right? So then among those 3, so you are going to have 5, right? Similarly here, this is a 3 in distance, you get 3. So the constraints are the following. First, the queries can be as long as 2 times 10 to the power 5. And the queries are unique. And this is the coordinate range, right? And the k is in this range. So this is a typical problem of using heap to solve the problem. So here, as we would like to find the case nearest obstacle after each query, right? So we store the negative distance of a point xy. In other words, this is a negative L1 distance. Once a new obstacle is made, if it were very near to the origin and the heap length is larger than k, so we push the current negative distance into the heap and pop the heap root element, so at 0. So here is an example to digest the idea. Assume k is 2, right? So we have -5 and -3. So now if we have a point contribute to distance, negative distance is -1, so which is corresponding to a closer distance, right? If we want to find the second closest one, so we should have 3, right? So we push -1 into the heap, so we are going to have such a state. But the length is greater than 2, so we need to pop out. So because we are going to use the Python implementation, so the 0 element corresponds to the smallest element, which corresponds to the largest distance, right? So we are going to pop out this -5. What left is a -3 and -1. So we are going to have -3, or the negative of -3, that is 3 to the second closest distance, right? So basically this if we follow this idea, so we can get a very easy solution. And also as a extra, we are going to provide another format of coding. So we are going to overwrite a less than down the method. So with that said, let's first write a standard solution. So in the standard solution, so we are going to use heap and maintain its length capped at the given length k, right? So now first we are going to initialize a result variable, which is an empty list. So this is going to hold each case shortest nearest distance. Then we initialize a heap. What's next is to do a traversal, linear traversal of the queries. So let's do it for I and xy in enumerate queries. Then we are going to push. So we're going to use this module heap push. Notice that we first push element into the heap. So here only the distance matters, or we can say only the negative distance matters. So we push just a negative distance. So the absolute value of the x coordinate and then absolute value of the y coordinates. So then if length is of the heap, actually we can use I to do this. So if I is greater than less than or equal to k minus 1, so the length of the heap will at most k, so nothing should be done. Otherwise we should do also a pop operation. So if I is greater than I minus 1, right, then we are going, so if you from 0 up to so not I minus 1, k minus 1, so you are going to get more than one k element, so we need to do a pop operation. So let's do heap q heap pop. So this way it's guaranteed that the heap can hold at most k elements. So first, if ki is less than k minus 1, so in this case we don't have k elements in the heap, so the result should append -1. Otherwise we have at least k elements. Then the top or the root element at the heap will correspond to the smallest one, which corresponds to the k's nearest distance. So what we are going to append is heap and 0. Notice that what we push into the heap is a negative L1 distance, so we need to put a negative sign here. Then we can return the result state. So this is the one solution, which is very short, right? So basically we initialize a result list and a heap list, and then we do a linear traversal. But in between, we maintain, we make the heap have a length capped at k, right? So now let's do a test. Heap is not heap push. We write 3p, so it's heap push. Here heap pop. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So this is the one solution. So if our purpose is only to solve this problem, then we are done, right? So next, we want to extend this coding. So we want to add some flavor of object-oriented programming. So we want to define a class which encodes the information about the points in the query, and then we can add that object directly to the heap. So, but in that case, we need to override the less than down the method. Let me so change this one into solution v1. Then let's write another solution. So here we want to object-oriented programming and override down the method. So here I can implement a method, let's say a class called point, right? So it can store, let's say, the point information, self x equals x and self y equals y. And then I want to define a less than or equal less than method. So self, this is a point object, and then compare with another point object. But we want this down the less than method tailored to this specific purpose. So here I define this. I will define if the absolute value of self, in other words, distance, L1 distance of self is greater than ABS px plus ABX py. In other words, if the L1 distance of the point self is greater than the L1 distance of the other object P, so we regard this as a less than relation, which is specifically defined to this problem. So now let's write the solution. So here, what I'm going to do, here I don't push in this a negative L1 distance. I push into the heap the points, right? This is the more object oriented, but actually for this specific problem, this actually implements slightly slower than the first version of solution. So here, this is nothing changes, right? And here, what we expand is nothing but heap 0. So notice that this guy is now a point object. So we want to get its L1 norm. Heap 0 y, right? So then we get the result. So essentially the same, but we make it more modularized. So let's look at the test. It passes one example. Now let's look at the generic case. You can see it's slower, but it also passes all the cases. This is a good practice, right? So in other words, we can override some methods to tailor our specific purpose. So this is for practicing of coding ability. Well, if we want to just solve the problem, so this one, version v1, is what we need. So with that said, I guess that's about it for the current video. Thank you.